All right. Hi, everybody. Welcome back to Office Hours. This is, I think, one of the last sessions. I think your exam's on Friday, so today and Wednesday would be the last ones. So we're almost there. We're almost there, which is good. So just a couple of things before we start. Today we're going to do this warm-up where we're going to cover or basically review SN1, SN2, E1, E2. So this is a blend of all the different types of problems we have seen so far. So we're definitely going to talk about all the major considerations that we have put into, determining which reaction does what. And then from here, we're probably going to go into the chapter 10 material, which is alcohols. I plan on finishing all of alcohols today. So hopefully you guys will be done with all of your exam material by today. And I'm still trying, so I think your exam's on Friday, so I might do an exam review Thursday. I haven't really figured that out yet if I will. And then you guys have a final, which is interesting. So I might be doing one more session next week, and we might just do like review of everything from the whole semester. So there might be a bonus session or two in there, but again, I'll just keep you updated. Okay, so the first thing is we're going to jump into these problems real quick. So for A, we see that we have this, secondary, I guess, starting material that I would say, and then we have this alkoxide anion, and it looks like a protic solvent with heat. Okay, so far I see that I have probably I would classify that as a weak nucleophile, a strong base. Okay, so do we all see why for A that's a weak nucleophile? It's a weak nucleophile because of all the branching that we see. It's heavy. Think that track example where you're running. Okay, so this is a pretty heavy nucleophile. Okay, so I'm thinking this is bulky, meaning that the nucleophilic properties aren't as great, but it still has those basic properties of removing a proton. Okay, so that's why I'm thinking this is probably going to go through an E2 reaction. So if you thought E2, especially, seeing this heat example could give you insight into the fact that we're warming this up to promote that E2 reaction. Anyway, so, what are the conditions for E2? Well, we need something called the anti-coplanar configuration. So don't forget that. Anti-coplanar configuration. Okay, so that essentially means that we're looking for a proton that is, adjacent to that leaving group, and specifically it has to be the opposite stereochem. So I'm looking for a dashed hydrogen. And luckily at both of those beta positions, beta 1, we'll just call that, and beta 2, there are these dashed hydrogens which are in the proper orbital orientation to be removed and, facilitate, that E2 product. However, we have to note that this is a rejuice-specific reaction because we're using one of the bulky bases. So even though I do have the proper hydrogen at the beta 2 position in terms of orbital arrangement, it's still not what I want because, this can't access that sterically hindered, tertiary center, but it can access beta 1, okay? So essentially, you can imagine that the mechanistic arrows would be the lone pairs on the alkoxide anion grabbing the proton at beta 1, donating that electron density into the ring, and then facilitating the removal of the bromine. So you're left with, the less substituted alkene product. So you'd actually get something that looks like this, okay? And this is my E2 product, all right? So that's all the things that I wanted to consider there. Remember, we had this secondary starting material, so, that's already my gray area. I see that I have this bulky base. We realized it was bulky because, it's that example of one of the examples that we know, terbutoxide or the LDA. And since it's sterically hindered, we can only access the, side of the molecule where there are less substituents. And then it was in that proper orbital configuration, the anti-coplanar configuration, to facilitate that removal. And if you didn't see that anti-coplanar configuration, I'm just going to draw a chair conformer real quick. So on position, let's just call that 1 and let's call that 2. So 1 would be the bromine going up, and then on position 2 would be the hydrogen going down. And if this was 6, it would be something that looks like that. And this was, okay, so that's me filling in all my substituents. So notice how both beta, this would be beta 2, and that's beta 1, have protons axial down. Okay, that's important. Okay, so that means that the orbital requirement is met for both positions. However, terbutoxide can't reach this beta 2 position because of that methyl group, but it can definitely reach this position, okay, facilitate that removal, okay, and that's why E2 can happen, okay, and this is partially positive, all right? So I just wanted to go over that one more time. Okay, so for B, Okay, so we haven't talked about what OTS is. We're going to see that today in the alcohol chapters, but essentially it's just a leaving group. So you can just imagine, for all intents and purposes, right now it's a leaving group. Okay, so let me draw a Newman projection. Actually, before I even draw a Newman projection, let's think about what reaction this pathway this goes through. Okay, so this is a secondary, starting material. Okay, we call that OTS as my leaving group. We know pH is benzene. Okay, so we have a secondary starting material. We see that we have this, I would say this relatively strong nucleophile, strong base, but we have something here. We have this protic solvent, and that protic solvent decreases the nucleophilicity of that. And I also see heat. Okay, remember, when we heat these things, we're also promoting it down the E2 pathway. So this is actually an example of E2. Okay, if the solvent were an aprotic solvent, maybe like DMSO, and heat weren't here, okay, so maybe if I just got rid of that and wrote DMSO, you could argue SN2. But because I have this protic solvent and I have heat going on, I definitely don't have SN2. I have E2. Okay, Keisha, does that kind of help you there? I know it's tricky. Okay, it's definitely not SN2. It would definitely be E2. Okay, so remember, it's that same requirement for E2 has to happen here. What if there was no heat, Leah? So if you're saying that if we had the protic solvent and no heat, it would still be E2 in that situation, because again, you would want to have increased nucleophilicity with the aprotic solvent. Okay, so yeah, it's still E2. And Abby, since that is not that bulky, can you get Zaitsev in this situation? Exactly, yeah, and you will get the Zaitsev product here. So Abby, you're looking to the future, you definitely see that. Okay, so the requirement, anticoplanar is still required here. So let's just draw a quick Newman to make sure that the proton on the adjacent positions could be removed. So on something we just want to take note of again is that we have two beta positions, beta 1 and beta 2. And this isn't one of the bulky bases that I know of. The two bulky bases that I know is tert butoxide, which is the one we saw above, or LDA, like we'll see in part E. So this is definitely not a bulky base, at least for now. So we can rationalize that we're still going to get the Zaitsev product here, like Abby predicted. We're still going to get the Zaitsev product. We're not going to get Hoffman. So let's just draw a Newman projection to make sure that we see this properly. So my front carbon looks like it has iso. I'm just going to draw iso because, we're being lazy here. And we have this proton. And then on the back carbon, it looks like we have OTS, probably a proton over here, and then this methyl group going down. So as of now, this is kind of what my Newman projection looks like. The front, we're looking at, with respect to the front carbon's proton, we're talking probably this one, okay? And then the back is the OTS, and notice that those two groups are not anticoplanar, okay? So what we can do is we can try and rotate the back carbon, maybe around this bond, okay? And keep in mind that same thing we've always talked about, WPD, okay? That's our way of, rationalizing our new stereochemistry. So I'm just going to reproduce this below so I have more space. So essentially, you can draw that same, front carbon staying the same. And then on the back carbon, what was wedge becomes plane. So now the planar is OTS, okay? And what was plane became a dash. So now we're dashed methyl. And then that dash substituent that there was none for the situation, but I guess you could say it was the hydrogen is now a wedged hydrogen. Okay, so I'll just draw it like that. Okay, let's just draw Newman here and let's see if we have a better orientation for our structure. So we have iso still going up. We have that benzene going into the board, okay? And now on the back carbon, we have what looks like this. Okay, so on the front carbon now we had, it was this proton and then OTS. Okay, so still not the orbital arrangement that I want for this structure. Okay, so let's maybe just rotate that again. Okay, so remember WPD. Okay, so, and this is literally just guessing and checking. Okay, so what was wedge now becomes plane. Okay, what's plane now becomes dash. Okay, and what was dash now becomes a wedge. So now it's wedge methyl. Okay, so this is the new Newman after rotating. Okay, draw another. Okay, and this is again the front carbon we're not touching, so it should be the same thing. Okay, but now it looks like we have the arrangement we need. okay? This is anti-coplanar with respect to the leaving group and the proton, okay? And that's what you need. Anti-coplanar with respect to the leaving group and the proton. Okay, so now whatever that base is this base is going to, so I guess I'll just draw it over here, this base is going to be able to remove that proton, donate the electron density, and then facilitate the removal. So the key is, oh, in here, I think I see a whole bunch of questions. Can you do this just by rotating the Newman and then transiting it to line angle? Yeah, you could do that as well. You can go that way as well. Could you rotate the front carbon? Yes, you could. And yeah, you could rotate the front carbon, and you could also just rotate the Newman and then just go directly to the line angle. That's also intuitive. Okay, so from here, you know that the proton that's right here is the one that's going to be removed. Okay, so again, I'll just reproduce the base. So the base is going to remove that proton, donate it into the ring, and form that. So really, what type of alkene you get is a Z alkene. Okay, do you guys all see that? If you wrote the E alkene, you'd be wrong. Okay, it's Z alkene. So if you trace your sigma bonding framework from that Newman, you see that you have up. Okay, so, oh, did I forget pH? Sorry. I totally dropped that. Just kidding. Okay, so then this would actually be an E alkene. My bad. E. Thank you, Charles. I didn't see that. Okay, E alkene. I dropped the phenol. Okay, so if you got Z, it'd be different. Sure, Caroline, what's your question?
So like, do you just have to rotate it until you get a Newman where they're opposite? And then how do you get the end product from the Newman?
Okay, so yeah, so the first part is right. So you definitely need to just rotate your Newmans until you get the leaving group and that, acidic proton anticoplanar. That's the goal right here. To get the end product, I'm really just looking to this structure, and you can see that the, basically, how can I say this? Let me try and think of a way to say this to you. Actually, maybe it'd be easier if okay, actually, I made a mistake. And this actually, thank you, Caroline, for pointing this out. So if you look at this example right here, basically you can look at the stereochemistry of your two groups. So if I have a dashed phenol group here, okay, and I have a wedged methyl group there, that means that those are on opposite sides of the sigma bonding framework. So essentially you can just draw the sigma bonding. Okay, so that's that, right? This is the sigma bond. And I see that the phenol is kind of going back into the page. So, I could basically say that the phenol is on this side, okay? And then you can say that, oh, the wedge is kind of coming out this way. So that could be, coming to the front. And then, that's my pi bond. So that's kind of where I'm at now. And notice that this is clearly an E format. That was just quickly from that. I see that the dashed phenol kind of goes in, and then the wedge kind of comes out. And clearly, with respect to this alkene, if I draw that line, the phenol is kind of on this side, and I can rearrange, the isopropyl for down here, okay? And then on this side, it's there, and the proton is here. So this is clearly an E alkene. So then you know what your structure looks like with substituents, and you know that it has to be E. So essentially, you could just go like this. You need to draw your alkene is going to go there. Your pH is going to go there. That makes sure that I have my E alkene, okay? That's how I would have done it from that. Yes, the phenol is definitely ranked higher. Okay, let's keep moving. Okay, so this would be the product for B. Okay, so for C, it looks like I have, a secondary material again, so we're still in that gray area. It looks like we have a strong nucleophile, strong base, and we're in aprotic conditions. In the chat box, what do we think? What do we think? SN2, right? This is SN2. Okay, so this is exclusively SN2 in this situation. We have a strong nucleophile, strong base, and it's enhanced nucleophilicity because of the polar aprotic solvent. So remember, this is backside attack, okay? So backside attack, this is azide, the bullet nucleophile. And since the front face is sterically hindered, it's going to attack first and then facilitate the removal of the leaving group. Remember, it's bimolecular. Okay, so essentially we're going to get, you know, a product where the stereochemistry is inverted. Okay, so dashed N3. Okay, and that's the product there. Okay, that's it for C. Pretty easy. Okay, so for D, we kind of see we have a secondary leaving material. Okay, I'm sorry, a secondary leaving group. And we have what looks like a strong nucleophile, strong base, but it's slightly reduced because of this polar protic solvent, meaning the nucleophilicity is slightly reduced. Okay, so I'm thinking this is yet another example of E2. Okay, yeah, good. If you thought this was E2, good. And I'm trying to do that, and if you got the trend, I'm doing a lot of E2 on purpose because it's the kind of the most difficult. So now there's no steric hindrance here in terms of, you know, being a bulky base. So we're still going to expect to get the Zaitsev product again, okay, Zaitsev. So, you know, in terms of beta positions, I have beta 1, okay, let's call that beta 1 and beta 2. But is beta 1 accessible in terms of having acidic protons? No, right? Not at all. So we're really only limited to beta 2. Okay, so if I draw in the hydrogen that's available at beta 2, and maybe if I drew my Newman looking up that bond axis, let's just convert that to my Newman. So I'm going to call that TBU, like terbutyl, okay? And then I'm going to call this just OTS. And actually, am I looking at this the right way? Oh, no, if I'm looking up that bond axis, let me just draw OTS there. This is the hydrogen. Okay, and then the back carbon, we have hydrogen coming out here. We have the methyl group going there. And then we have, like, I'll just call it cyclo for the thing going down. Okay, so clearly, these two groups are not anticoplanar. So let's just do it the other way that some of you guys were saying. What you could do is you could just rotate the back carbon. Okay, so let me just reproduce that. TBU. This is the front carbon. We're not changing it. You could just rotate the back carbon such that the OTS is going to be 180 degrees from this proton that we see back here. So I'm going to rotate the back carbon such that we get hydrogen there, H3C here, and the cyclo there. Okay, so that's all I'm doing is rotating it such that I get that anticoplanar configuration for, you know, the leaving group and that acidic proton. Then from there, you can just convert this into, you know, back to line angle. So that's, you know, this trans framework, you know, with terbutyl up here, that, you know, methyl group going down. In terms of that front carbon, the OTS was here, I guess. Now I'm going to reproduce it like this. OTS was here. On the back carbon, it also looks like you had that wedge, and then what was the cyclo thing? Yeah, just, I guess, okay, so wedge cyclo thing. And then on the back carbon, it was dash hydrogen, okay? So this is the format that you needed. And then that base, I'm just gonna call it B minus, oops, is going to grab this proton, donate the electrons in and facilitate the removal, okay? So now if you can kind of rationalize what this is going to look like, it's going to be, so the wedge is kind of indicative of it coming out towards the front. Okay, so something, oh, sorry. Okay, so do you guys like that? So essentially the wedge is kind of indicative of coming out towards the front. That's there. So you can kind of rationalize that you're going to get this, I guess you could say E alkene as well over here. E alkene. Okay, not Z. Okay, so if we know it's E2, we should draw the Newman we want with coplanar and then redraw the pressure. Exactly, that works, Lauren. I like that. Okay. Yes, E2. It's E2 again because this is a strong nucleophile, strong base at first, but we have this polar protic solvent, so it slightly reduces that nucleophilicity there. So this is going to be E2. Okay, so it's more of the basic side than the nucleophile side. Okay, LDA for E. Okay, LDA is one of those bulky bases. That's again another example of E2 exclusively. Okay, so it doesn't matter about, you know, this beta position because it's sterically hindered. So we're going to remove from this position. So essentially, you can go right to the product. This is easier, and you're going to get this kind of situation. Okay, pretty easy, just because of its steric hindrance. Okay, Then for F, what's happening here is we have this tertiary starting material. Okay, so clearly that's a good hint that we're going to go through an SN1, maybe E1 pathway. We have a weak nucleophile, weak base. So yep, this is going to leave on its own. This is going to go through SN1 and E1. Okay, so then you get this kind of tertiary allylic carbocation, and then that methoxide, that methanol group can either attack it or it can remove a proton, okay, from here to, let's just draw that over here, CH3OH. So it could do this to form the elimination product. So you actually get this structure for the elimination product, or it could have attacked at that position to get this ether. Okay. So you get the SN1 and the E1 products there. All right. So this was kind of a combination of everything. If you're overwhelmed, that's okay. Like this is the hardest thing I think really for me in Orgo 1 and 2. Okay. So this is very intellectual. You have to really see your reaction conditions. But yeah, this is kind of where I'm at with chapter 9 material. All right. Def overwhelmed. It's okay. All right, it's gonna be okay. Let me see what else is going on in the chat box. You can determine easy configurations basically by looking at the wedges and the dashes on the line angle. That's also a shortcut. So if the wedges and dashes line up, meaning both wedges, and they have to be on the same base, that would probably say Z. And if wedges and dashes were opposite, you know, and that was present, that would probably be indicative of an E configuration. The whole paper, this is kind of, I can show it in sections if that helps. Maybe actually I can look it up. I don't know if you guys want to screenshot that. Okay, I don't know. So that's kind of where we're at there. Let's move on to some other, just maybe we can just talk about some key things here, I guess. Okay, so remember SN1 and E1 always happen. Okay, always together. Okay, so essentially what that means is we're going to have probably and X is just a leaving group, so X equals some sort of leaving group. We have some sort of, pretty substituted, starting material where the rate determining step, okay, is dependent on this leaving on its own. Okay, so if that leaving group can leave on its own, okay, we get this carbocation intermediate. That was the key. It's prone to rearrangements. Remember, we always have to think about any potential rearrangements. And from this key intermediate, that was the key because we used some sort of weak nucleophile, which also satisfied the definition of a weak base. Okay, examples of that were things that were not charged. So, typically we saw, methanol. Methanol is a great example of a weak nucleophile, and it's also a great example of a weak base. So that's why you get the elimination product as well as the substitution product. So if you want the substitution product, those mechanistic errors would be in red, and I'm going to skip a few steps, the depronation step, and you basically get an ether. Okay, so something like that. You also at the same time get the elimination product because it acts as a base where, this adjacent proton can be deprotonated, that electron density can be donated in, and you get this kind of olefinic, or I should say alkene, end product. So that's why SN1 and E1 always happen, right? Let's kind of see the opposite of what happens under SN2 conditions. Okay, so SN2 conditions, we know that we were, pretty limited to this, sterically unhindered starting material. So we had the sterics argument, okay? And the rate determining step was actually bimolecular. That's why there's a 2 in the name. And we were dependent on some sort of strong nucleophile, strong base. Okay, so strong nucleophile, strong base. So examples of that were, something with a negative charge on it. So maybe let's just show the deprotonated version of what we saw above. So maybe sodium methoxide, something like that. And to increase the nucleophilicity, we use some sort of polar aprotic solvent. Okay, and it was aprotic, meaning it doesn't transfer any protons to this methoxide nucleophile, so it ensures that it's as strong as possible. Okay, so examples of that were DMSO, DMF, etc., you know, acetonitrile, things like that. And actually the rate determining step was bimolecular, where the nucleophile comes in and, you know, facilitates the removal of the leaving group. So this is when you had something like the inversion of configuration. So in this situation, we weren't chiral, but you would expect inversion of configuration. And we know we also go through this trigonal bipyramidal transition state. Okay, so those are some other key things to remember. Okay, so that was the SN2 pathway. So that's how we were able to, you know, promote that means. And then when we were in between, when we were at the secondary, so this was, you know, tertiary and this was primary, but when we were in between at the secondary, we were like, okay, we have to kind of think a little bit harder. So let's just use maybe, you know, this example. This is secondary. And, you know, if I were to say, let's just do water, okay, you'd almost definitely say that that would be SN1, okay? But then let's say I wanted to do, you know, something like sodium azide and DMSO, okay? That would exclusively be SN2. Okay, so we had this competition when we could change the reactant pathways to go through the different nucleophilic substitution products. All right, so is everybody kind of clear on the differences there so far? Okay, because how does E2 happen? Okay, so E2 is the tricky one. Okay, so it's in competition with pretty much everything, I would say. So, and what we could do is, you know, before we had this, where should I do it? What did the SN1 versus SN2 said? What I was saying is we had, you know, competition here by changing, you know, actually, I guess it's best maybe if I used, here, sodium hydroxide and compared it to water, okay, because this is just the deprotonated version, okay, right here. The hydroxide is just the deprotonation version of water, and I enhanced the nucleophilicity by using a polar protic solvent. So really, all I did was change the solvent conditions here, and by changing the solvent conditions, you know, water's its own solvent, I can basically change the pathway to go from SN1 to SN2. Okay, so that's kind of the key difference here. Okay, and then in terms of E2 stuff, what we saw is you could go from, you know, this tertiary, if we had this tertiary starting material and we had, you know, some sort of bulky base, okay, we could basically do an E2 reaction. So we could say that we had, you know, some sort of bulky base like this. Okay, this is an example. Okay, bulky base like that. We have another example, LDA. And what that can do is it can, you know, facilitate the removal of the leaving group by, you know, removing like a proton out here, like a beta proton out there. So, you know, this is still a tertiary starting material and we could still promote E2, okay? But then we could also do it with, you know, a less sterically hindered, you know, product, maybe something like that. And we could promote E2 by using, again, some sort of strong nucleophile, strong base, but we reduce the nucleophilicity by adding some sort of, you know, protonated solvent and obviously heating it. Heating it promotes E2, okay, it agitates it, you know, gives you more energy to do this. So essentially you can promote the E2 pathway by removing a proton, donating it in, and facilitating that, okay? So E2 happens, you know, pretty much all across the board. So you just have to really look at your reaction conditions to basically see which one's happening when, okay? I'm going to keep moving on to the new stuff because we spent a lot of time on, half the time on that old stuff. Again, watch the old videos if you are still not clear on this nucleophilic substitution, beta elimination stuff. And if you're having trouble with it, know that that's okay. This is typically the hardest stuff anyway, out of the whole class, in my opinion. All right, so we're going to move on to alcohols. Okay, so chapter 10. Chapter 10, alcohols, okay? This is a fun chapter. I think it's pretty easy. I think it's relatively like chapter 6 and chapter 7. So if you like that stuff, we're gonna go back to that. So essentially, I'm gonna skip nomenclature. Again, you're just gonna change the ending to all, OL now. That just indicates that an alcohol is present. So for instance, you know, this, we've seen, you know, this is propane, you know, because it's an alkane. We've seen, you know, propene, okay, propene. And you can also see propine, okay, propine is that. So we've seen all of these endings, and now we introduce all. So if there was, you know, maybe an alcohol on the secondary position, you would say that this is, you know, Obviously, it's not chiral, so you could say 2-hydroxy, okay, prop, pan, ol. Okay, you drop the E and you add ol. So 2-hydroxy to indicate that there's a hydroxyl substituent, and propanol. Okay, or you could just call it 2-propanol. I think you guys are used to 2-propanol at this point. Okay, so essentially that's like just the new stuff that we're adding. We're just adding ol. Okay, so that's it for nomenclature for me. Okay, so then the first thing is we're going to basically learn how to form alkoxide. So we're going to jump right into reactions, which is great. So reaction number 1 and 2 are going to be paired together, and you kind of already seen this. So we know that we can do alkoxide synthesis, or at least we know that we've seen that type of anion before. And what it is it's basically like we have an alcohol, okay, and we know that these alcohol protons that are attached to these, oxygen heteroatoms are relatively acidic, because we talked about how there's this dipole moment towards the oxygen, and if I were to deprotonate that, the oxygen gets a negative charge, and that's okay because the oxygen is relatively electronegative and it's stable, it likes that. So if I were to treat this with some sort of base, okay, I'm able to deprotonate that proton and generate the anion of that alcohol. And this is the alkoxide anion. And you've heard me say that a lot so far, alkoxide anion, okay? And then you also get some sort of HB waste product, okay? And there are 2 different ways that we're going to show you how to make the alkoxide anion. One, I'm going to show you how to do it mechanistically, and the other one we're not going to require. So the first one is my favorite one. I think it's the easiest. Okay, so this is reaction 1, and it's upon treatment of a metal hydride. So essentially, I can say that same alcohol starting material, and this is the reagent. So it's some sort of metal, so sodium, potassium, things like that. And I'm going to attach it to hydride. So if I were to resolve these into their ionic components, it's sodium cation and it's hydride anion. So H with a lone pair attached to it, okay? And hydride, this is hydride, and it's going to act as a base. It's a really good base, and it forms H2. So essentially you can see that mechanistically that base is going to grab that proton for reasons we've just talked about. There's a dipole moment towards that oxygen. Okay, and then that electron density gets retained by that oxygen, things we've all seen before. So we're very nicely able to generate this alkoxide anion and generate H2 gas. And this is, thermodynamically favorable according to Le Chatelier's principle, because you can imagine that this H2 gas just bubbles away in the reaction vessel. So it bubbles away. So, you're shifting your equilibrium to the right because you're taking away a product. You remember when you take away, you're shifting your equilibrium. So this is a very favorable reaction, actually. The fact that you form this gas, that kind of leaves the solution. Anyway, that's part 1 of how to do this. And there's another way to do this. You can actually take that same starting material and you can treat it with pure alkali metal. So that it can either be, and it's always 2 equivalents. So this is how we indicate that with a degree sign. Or you could also have said, 2 equivalents of pure lithium, things like that. And they're all kind of interchangeable. They do the same thing. We don't know the mechanism here, but essentially you get this product as well. Okay, so either use the sodium hydride or the pure elemental form. Remember, it's 2 equivalents. This one we don't cover the mechanism. These are 2 separate reactions. Yes, this is reaction 1. This would be reaction 2. Both get to the same product. For me personally, always just use the first one because the mechanism. It makes logical sense to you. You will get full credit on here. So if asked, I always kind of show this one. This one makes the most sense to me. Okay, 2 separate reactions. Okay, and then from there, you can treat, that alkoxide anion maybe with some sort of haloalkane, maybe like Br, and do it under, aprotic conditions, and you can get, Williamson ether synthesis. So that's what we call Williamson ether synthesis. You don't have to know that name, but it's a way to form ethers. We know that that's going to be an SN2 reaction because it's polar aprotic, and essentially you extend the carbon chain by 2, so 1, 2. Okay, so you get diethyl ether. So diethyl ether. So essentially, you can see that forming alkoxide anions is a very useful tool in synthesis if I wanted to do an SN2 pathway. Okay. Abby, you can already see where we're going with this, okay? So that's kind of where we're going. So the first thing is forming these alkoxide anions. I think they're pretty easy. Okay, so just deprotonating that acidic proton, all right? So let's just do some examples in the student workbook. So I'm just gonna go to, I think we should just do C and D probably. So this is page 11, number C, so, or letter C. So we have this hydroxide. Step 1 is sodium hydride, and step 2 is going to be ethyl bromide. So I'm just going to go to that line angle, and it looks like DMF, right? Dimethyl. And so again, I'm just going to draw this solvent so you guys know that. Again, this is DMF, that's the solvent. Okay, so essentially sodium hydride, pretty easy. We know that's the base. This is kind of an acidic proton. So the product of step 1 is just going to be the alkoxide anion. This is the isopropyl derivative. Okay, so this is just the product of step 1, product of step number 1. Okay, and then from there, you see that you have basically what looks like an SN2 reaction. You have a polar aprotic solvent, a sterically unhindered, starting material, and, a really good, strong nucleophile, okay? It's not tert butoxide, that would make it weaker, but this is not a bulky base yet. So essentially, you can imagine that the product is going to be an SN2 product where we extend the carbon chain by 2 carbons, okay? And that is my end product, another ether. So that's C. Okay, so for D, it looks like we have this olefinic starting material. Olefin just means alkene, if you hear me say that. Sometimes we'll just use that word. Water, HCl. We have 2, sodium hydride. And 3, we have what looks like cyclic structure and acetone. Okay, again, for acetone, it's for nail polish removal. Nail polish remover, tongue twister, that's what it looks like, acetone. All right, so first step, it looks like treating this acid catalyzed hydration condition. That's easy, so that's just gonna form an alcohol, Markovnikov, on, the secondary position. Okay, so then from step 2, you probably treat it with a base, so that's gonna give you the alkoxide anion. And then you extend the carbon chain in an SN2 fashion in step 3, by adding 1 carbon and then the ring. So it becomes 1 carbon and then the ring. Boom, another ether. Okay, so this is Williamson ether synthesis, okay? You actually do this reaction in the Orgo lab, okay? So you guys will do this with the reflux condenser, pretty cool. And yeah, I think that's good enough. Okay, so that's kind of the first reaction at play. Okay, so the problem now that we're going to see with alcohols is this. Let's say I had hydroxide, and I were to treat it with sodium, azide, and DMF, okay? And then let's say I were to do, this. And then this is a purely hypothetical reaction, okay? Okay, so here we are. So essentially, in the first example, what are we predicting? What type of pathway? SN2, right? Okay, but the problem is that SN2 really isn't going to happen here, okay? So up until now, we think SN2 is going to happen. We have a primary, starting material, and we have this strong nucleophile, strong base, enhanced nucleophilicity because of that polar aprotic solvent. But what's happening here is we actually have this relatively bad leaving group. This is a bad leaving group. And that, if there's one takeaway to take from the chapter 10, material, it's that alcohols are terrible leaving groups. Hydroxides are terrible leaving groups. So, if I were to show that, this is just a hypothetical, and you generated hydroxide, yeah, you can argue that it's kind of stable from that negative charge on that oxygen, but it's really basic and charged, and it's not a good idea. It's really just not stable. What would be stable is if I had, the resonance version, the carboxylate anion, maybe something like that, where we could show some resonance. But again, this is not stable on its own. So what we're going to do is, in the next series of reactions, we're going to see ways that we can make that alcohol a good leaving group and then perform reactions on them, okay? So the first reaction in this chapter was just deprotonating to form alkoxide anions, showing them in SN2 fashions. Now we're just going to be able to play with those leaving groups and make them better, okay? So one of the ways that we can do that is we can protonate. So we can actually protonate that alcohol to make it water, okay? So now protonated version, and then subjecting it to sodium azide, okay? So the azide now can do an SN2 fashion, okay, nicely, and then your byproduct is neutral water. Now remember, we said neutral is so much better than charged, So notice how this is a more successful reaction. You have more of a product gains than this one because we went through a nicer, leaving group, okay? So that's kind of the whole point of what we're gonna see with the following material, okay? So, here. So reaction 3, so we showed reaction 1 and 2. So reaction 3 is going to be acid catalyzed haloalkane synthesis. Haloalkane synthesis. I'm making kind of this name up, but essentially you have some sort of alcohol and you treat it with some sort of acid, and that's able to make some sort of haloalkane, okay? Something to note in this reaction, SN1 and SN2 happen, okay? And this, you may not think that that's important to note. It is important, okay? So just kind of take that for what it is right now. SN1 and SN2 are happening here in this reaction. So we're not limited in any way to our starting material. So let's show some examples of that. Excuse me, I keep yawning. So we have this, let's say this is the primary alcohol. Okay, this is the primary alcohol. And I'm gonna treat it with some sort of, halogen, maybe some sort of acid. Maybe let's just do HBr, okay? And then let's take another example. Let's take, a tertiary version. So, and do the same thing. And actually, let me do something better. Let me show some stereochemistry, okay? So if I were to consider the stereochem here and trace that, that'd be a 1, 2, 3, 1, 2, 3, 1, 2. So I'm getting S configuration, okay? I'm getting S there, okay? So hopefully we're here. So let's just kind of draw mechanistically what we think happened. So we know that this is kind of an amphoteric substance. It's analogous to water. It's almost like it's a homolog. And essentially that, just as much as that proton can be deprotonated, this lone pair can also grab a proton, okay? So we can imagine that, this is the first set of mechanistic arrows. It's converting that, bad leaving group into the protonated version, which is water. And we know why water is a good leaving group. Water is a good leaving group because once it leaves, it's a neutral byproduct. That's why life exists on Earth. It's like water is a stable species on its own. So this is one of the most useful reactions we know, is turning that alcohol into the protonated version, which is water essentially. And then we generate free bromide, okay? And then what do we think mechanistically is going to happen here? We have, this primary, leaving group, and we have a relatively good nucleophile. So SN2 is the correct answer. So then mechanistically in blue, it's going to attach that carbon, facilitate the removal. This was an SN2 example of this reaction, okay? Plus water. Okay, so that is the SN2 version. But likewise, we can see an SN1 version. Okay, so here, the same thing happens. So a lone pair is going to grab the proton, okay? It becomes protonated. So essentially you get that, water. And then what happens is now the rate determining step isn't dependent on the bromide coming in. It's actually an SN1 fashion, where that leaving group will leave on its own, okay? You get this tertiary carbocation. This is the SN1 fashion. And what happens is yes, you could argue a little bit of E1 does happen here, but it's a minor product in the sample, so we're going to disregard it. And essentially, you can say that the free bromide can now come in and attack, and you get a racemization of haloalkanes. So you get, this bromine on a wedge, and you also get the bromine on a dash. Okay, so this is yet another example of converting an alcohol to a haloalkane, and you know that it can go through either SN1 or SN2 pathways. Okay, so now I think you guys are looking towards the future. So let's say I have this, and I want to go to, let me think, let me just draw a synthesis real quick. And okay, cool. And I want to go to that, okay? And this is the only starting material you can use, okay? So you're going to use this twice. This is the only starting material. And I'll give you a hint. You're going to use this twice, Okay, so everybody take a second. This could be how your synthesis is provided. Okay, this is your only starting material and you can do it twice. So I'm thinking I need two things, right? I'm just think to yourself for a second. I need a 2-carbon alkoxide anion, okay? Up until this point, I know that I could probably use some sort of alkoxide anion and then probably adding it into a 2-carbon, haloalkene. So maybe something like that, right? Because that would give me this product. Do you guys see that? And I can clearly get to that product somehow. So let's first think about how I can make this alcohol. Actually, maybe I just made this up in my head. Maybe I have to adjust this. 1, 2. Actually, yeah, let's just start here. This is your only starting material. Oh, I made this up. I don't really like it. Okay, well, let's just go with this. Okay, so essentially, how can I make this alkoxide anion? Essentially, you can basically take the alcohol version of that, and you could have treated it with the sodium hydride. Remember, oops, down here. That was a way to get this hydride into that alkoxide anion. And then how could I have gotten that? Well, I could have started with some sort of alkene, okay? And I could have done, it doesn't matter which reaction I did to this because no matter what, you would get an alcohol at one of the ends. So I could just say, H2O and acid, okay? So that's one way of getting, from this alkene starting material, that alkoxide anion. And then if I were to use the same thing, how can I get that? Well, we know that we can do probably H2 and platinum to reduce it. So that's probably H3C, CH3. And then I could probably Br2 and light it, okay? Because we know that radical reaction, and then that gets me a bromine at the end. And then you could put those two together, all right? So that was just, you guys can kind of see your ways into synthesis now. You have a lot more possibilities than the chapter 6 and chapter 7 reactions, all right? But the key is to know that your end products in these reactions are going to be in SN2 fashion, most likely. So you'll probably see 2 fragments, something like that. Or it could be an SN1 thing where a nucleophile comes and attacks later. Okay, so just kind of opening our eyes there. Anyway, so just going back to what we were saying is we can convert these alcohols into haloalkanes by just using some sort of acid, and they follow both the SN1 and SN2 pathway. All right, let's keep moving. So there's other examples. Let's just do some examples of that. So we're on page 111. This is G. Okay, so the first thing is it looks like hydroboration oxidation. Okay, and notice how we're using all of these old reactions again because you do have a cumulative final. And like I said, in Orgo 2, all this comes back. So this is anti-Markovnikov addition of an alcohol. So you should get the alcohol at the primary position. And then what do we think? SN1 or SN2 for the haloalkene conversion in step 3? What do you think? SN2, right? Because the proton is going to basically make this water from that acid. And then this is primary, and that's a good nucleophile. So it's going to attack there and kick it off. So essentially you get this nice haloalkene at the end. And just always write to yourself that was SN2 in case we have any questions later on about it. And all the same things that you learned about SN2 still apply here with the alcohols. Inversion of configuration, trigonal pyramidal transition state, rate determining step is dependent on the concentration of the acid and that intermediate, things like that. That'll all apply. All right, keep going. Let's see another example. So let's just try letter I. Okay, so in I we have, what looks like this vinyl cyclic structure. Okay, and then step 1, we have OGAC2, THF. So this looks like oxymercuration conditions. This is the reduction step. We don't know the mechanism. And 3, we're just going to say is HBr. Okay, so essentially what we can imagine is we get an alcohol at the secondary position. Okay, did this go through a carbocation intermediate up until this point? From step 1 and step 2? No, right? Because remember, the key of using oxymercuration, demercuration was we never went through that carbocation intermediate. So we successfully formed this Markovnikov alcohol, essentially. Then in step 3, we protonate it, okay? So now it's basically water. And then actually here, you can say that it goes through an SN1 and it kind of argue SN1 or SN2. So most likely it will go through an SN1 pathway. And this is, I made this question up. We would kind of give you a better question in the sense of showing The reason why I'm saying it's SN1 is because it's also protic. Even though we're using acid, there's a whole bunch of protons here. So this is kind of my way of telling you it's SN1. So if that leaves, you get this vinyl or adjacent carbocation. What do you think is going to happen? Oh yeah, a ring expansion, and then the bromine can add there. Okay, so now you get 4 major stereoisomers. Okay, so again, all those carbocation rearrangements still can apply, even though it didn't happen in step 1, it did happen in step 3. So you'd have a whole bunch of products forming there. Okay, again, all that still applies. All right, so there are 2 other ways that we can make alcohols into haloalkanes. Okay, so the first way was treating it with HX. So far, let's kind of recap where we are. Recap of chapter 10. So we have reaction 1. That was, I'm just gonna say ROH, and we showed sodium hydride, and that made RO minus, and sodium ions hanging out, and H2 gas, okay? Then reaction 2 was another variation of that. You could take ROH, and then we said use 2 equivalents of that pure metal, and somehow you also get that same alkoxide, okay? Then reaction 3, we basically said that we can take that alcohol and we can treat it with some sort of acid like HX, HBr, HCl, HI, and then you can essentially convert it to RX, okay? RX and then some sort of byproduct, okay? And that could form, either SN1 or SN2. We've seen that. We've seen both examples of that. Now we're going to see 2 more ways that we can form RX from ROH, okay? And these are exclusively going to follow SN2 pathways, okay? So reaction 4 and 5 are both going to follow the SN2 pathway, whereas this one followed both, and that's kind of the key here. So ROH, and then the first one is going to be using phosphorus tribromide, okay? And you're going to get, and you can tell that's a source of bromide, so RBr, okay? And then over here, reaction 5, we're going to convert this with something called thionyl chloride, SOCl2, to get RCl, so that's the source of chlorine, okay? And both of these exclusively follow SN2. So I think that's the key here from this chapter, is noting that if it's SN2, you're limited to, that primary or secondary starting material, and that's the key. Limited to primary/secondary starting materials, okay? Whereas this reaction, you were not. So I think you can kind of see that no limitations here. So I think you can see how in synthesis, we might be tricking you here with your selection of reagent. You might be like, oh, I can use HBr, but oh no, you really can't, because throughout your mechanism, you might have, gone through an SN1 pathway and it got that extra stereoisomer, where in the synthesis problem, we said we only want this one type of enantiomer. So this is kind of a big hint, in terms of which type of reagent to use when you're converting to haloalkanes, okay? So maybe I would write this on your paper, wink, 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 synthesis. Okay, synthesis, and we'll do some more examples of that on Wednesday. Okay, so let's kind of just jump into reaction 4 and 5. So let me grab some paper. Okay, so the first example, and I'm just gonna, let's just use J, letter J. So I'm on page 112, we're just using page 112, letter J. So essentially you have, this wedged hydroxyl. Now we're gonna show you some stereochem, and we're gonna treat it with phosphorus tribromide. Okay, this is something where, again, another Lewis structure I would know, so I think there's only been 5 total structures in now at this point. Okay, so phosphorus is prosperous. Okay, it can exceed the octet configuration if it needs to at some point. So right now we are at, this configuration, and essentially what you can happen is actually, I think it's actually okay without, let me just double check, sorry, this is important. I don't know if it has a lone pair or not. Phosphorus tribromide. Yes, it does. Okay, it's trigonal bipyramidal. Okay, yeah, so it does have this lone pair. So essentially it can accommodate more than 8 electrons. Okay, it's in row 3 and lower, so that means that, it has these extra d orbitals that can house that, but beyond the scope. The point is that this is the Lewis structure that you need to know. And again, this is amphoteric, so this is the alcohol acting as a base. And what's going to happen is it's going to attack this phosphorus to form this really kind of bulky leaving group. Okay, so essentially what happens is that series of mechanistic arrows where there's an oxygen phosphorus forming bond, okay? And then you also have this phosphorus bromine breaking bond, okay? So essentially you're gonna be left with this really bulky material, okay? So you can see how we would have, now a bond to phosphorus with the 2 remaining bromines, okay? Okay, this becomes charged on the oxygen position, okay? And we're there, okay? And we have free bromide hanging out. So you can see that we converted, this is basically the equivalent of converting it to water. Anytime you make it positively charged within the molecule, you're converting it into a good leaving group, because if it's positively charged in the molecule, it means it has too many bonds. So when something comes in to kick it out, it's gonna lose that extra bond and return back to a neutral state. Okay, so if it's positively charged in your conversion, like you are doing here, just like what we saw with converting it to water, it's going to become neutral when it leaves. So now this is the SN1, SN2 fashion. Because of the sterically hindered orientation of this now good leaving group, we could only attack from the back face. So this is why it's SN2. And then you exclusively only get this one stereoisomer, where the bromine is on the dash configuration, and you have this, byproduct, which is Br2POH. Okay, that's the byproduct, and it's neutral, so that's why that's the driving force for this reaction. Okay, so yes, you could have also been like, so here's this situation with, with synthesis. If Dr. Peterson on the test were like, okay, I have this, and I don't know how I'm gonna go there, but essentially, I want you to give me just this, okay? Or, okay, I'll move it here, and then, or I could say, I have that, arrow, and I basically say, I'm racemic. Okay, that's kind of the trick here. If it's just this, you have to use PBr2, okay? Because you exclusively get that one enantiomer, stereoisomer, because of the inversion of configuration that is the SN2 pathway. Here, if it's racemic and you have both of them, you could just do HBr, because this is a source of bromide, okay? But what happens here is, remember, once this gets protonated, you could say that, oh, this leaves on its own, which forms a racemic mixture, which means that bromine can add on the front or the back face, okay? So you can see that these are just different ways of manipulating the stereochemistry from the stereoisomer that you were given in the start, okay? So there are multiple ways of doing the same thing, but the stereochemistry is what's really being focused on here. Okay, and the same thing happens with thionyl chloride, but it's just going to form a chloroalkane instead. Okay, so let's kind of see that. So let's move on to, let's just try like O or something. So this is O on page 113. So we have this kind of structure, and thionyl chloride. So thionyl chloride, another Lewis structure you should know. So it's actually something that looks like this, thionyl chloride. So it's like a carbonyl, but with a sulfur there, so thiol, and it has these 2 chlorines attached. So that's the Lewis structure. And again, it's the same mechanistic arrows where we have that happening, okay, and this happens. Okay, so this is actually a little bit different in terms of mechanism, but watch. So because we didn't have a carbonyl before, where's that paper? Oh, it's right here. Because I didn't have a carbonyl before, a whole bond was broken and that bromine anion was generated. Here, because I have a carbonyl, I don't have to break the chlorine yet. I can just kind of shove those extra pi electrons onto the oxygen. Okay, so that's kind of a little bit of a difference here. And you get this now really good leaving group. Okay. So we're here, that's my intermediate. And what happens is we have this kind of internal rearrangement. So internal rearrangement, because look at all those charges. Look how unstable that is. That's not good. So let's have an internal rearrangement to make this intermediate just a little bit more stable. And essentially it's the negative lone pair resonating back down. We kicked it up before, but now we're gonna kick it back down. And which one is the better leaving group? Well, the chlorine or this whole, bulky material, it's the chlorine. So this resonance of forming that, that lone pair coming down facilitates removal of that chlorine. And then now you're left with okay, and now you have a source of chlorine. So now in the same SN2 fashion, okay, in an SN2 fashion, it's going to do that. And that's SN2. And you get exclusively that. Okay? And then your byproduct is going to be SO ClOH or something like that. And again, another stable neutral leaving group. So the whole point in this reaction is we can exclusively get just this configuration by going through this pathway. But if you wanted both, let's say it's racemic, again, if it's racemic for the chloroalkane, you could have just done HCl, okay? And you would have gotten both. So again, just another way of exclusively getting that one configuration. So to recap where we are, we just kind of finished reactions 1 through 5. So again, reaction 3, you get a mixture of SN1 and SN2 pathways, so you kind of, there's no really limitations here. But if I exclusively wanted one type of product, like a wedge or a dash, it's a good idea to go through the PBr3 or SOCl2 ways. And again, we're limited to the SN2, fact or conditions that, apply, meaning that we can never do this with a tertiary. So by that I mean, this reaction does not happen. This does not happen, okay? That reaction cannot happen, okay? Exactly, Lauren, you got it. Yeah. Okay, so that's kind of it. And I think we have, honestly, we could finish, but yeah, we're gonna keep going. So if you guys can just stay, I think we'll be done in 5 more minutes. So that's basically reaction 5, okay? So then now after this, what we're gonna see is something called alcohol to Ariel sulfonate conversion. This one's actually really nice because you don't have to know any mechanism. So reaction 6, okay? So ROH, we're gonna treat it with something called Tozo Chloride, and we're gonna get ROTS, okay? So this is just another example, okay? And remember, we saw this kind of earlier, what it was OTS, so I'm just gonna draw a generic example. So let's just say I have, this alcohol. And what we're gonna say is we're gonna treat it with something called Tozo Chloride, okay, that's Tozo Chloride, and Pyridine, okay, Pyridine. And what Tozo Chloride looks like, so Tozo stands for toluene, but with a sulfur. So toluene is just a benzene with a methyl group. And Tozo Chloride just means it's a derivative of thionyl chloride. So it's basically, I think it's something like this, if I'm remembering it correctly. I think it's, yeah. So that's Tozo Chloride, okay? And Pyridine. So Pyridine is just, again, the solvent in this case. I think Pyridine looks like, I think it's aromatic like that or something, whatever. So Tozo Chloride and Pyridine. So basically, you don't need to know any of that. All you need to know is that what this is going to form is some group called OTS. And specifically, that the stereochemistry, the key here, is that whenever you see the Tozo Chloride reagent, the stereochemistry is retained. So notice that all the details really just come down to stereochem. So the stereochemistry is retained in this reaction. So if it's a wedge, it's going to be a wedge in your product. So how do we draw this? Really easy, just accept it. OTS, capital O, capital T, lowercase s, okay? And it's just basically a good leaving group. It has the benzene, it has the sulfur groups, so that's basically what you're imagining you're adding on to this, and it's basically a really good leaving group, okay? So basically, if you wanted to, manipulate stereochemistry for some reason with this, you could go through this pathway. So that's all you really need to know for this reaction. This is called an Ariel sulfonate. Why is it called an Ariel sulfonate? Well, it has this benzene ring, which is aromatic, and it has this sulfonate group that's on it. So you're basically converting the alcohol into this big, bulky Ariel sulfonate, which is analogous to saying that it's a good leaving group. So that's really kind of the whole point here. It's just a specific example of that. So let's kind of just see some examples of this. So we're just going to go to, U, I guess. Let's try U on page 114. And yeah, so we have this. We're going to have LDA. We're going to have BH3, THF. Step 3 looks like sodium hydroxide and hydrogen peroxide. Again, old reactions, and then 4 is going to be just Tozo Chloride and Pyridine. Okay, so LDA is a bulky base. We're going to imagine that that's going to be the E2 reaction. Okay, so E2 would basically just form the Hoffman alkene. So I'm thinking something like that. Okay, well, this is, step 2 and 3 is clearly hydroboration oxidation. So I'm getting the anti-mercaptan alcohol from that. Okay, so something like that. And then step 4 is just Ariel sulfonate conversion. So I just know that that goes to OTS. Since here there's no real stereochemistry to consider, end product. And you might just get asked that on the test, and if so, like, that's all you have to do, OTS. I just know that you rate OTS, that's it. All right, so let's try W. Okay, or I like how you said the one that I didn't say. So Keisha wants X, so we can do X. Okay, so we basically have this. And basically we're gonna say Br2. Okay, so that's a radical reaction we've seen. For 2, I don't know if we've changed it on your paper, but it should say LDA. So convert that to LDA. What does it say, Keisha? Does it say triethylamine or LDA? Anybody know? Does it say LDA or triethylamine? Okay, yeah. Triethylamine is just, it's a bulky base I use in my organic lab, so I'm familiar with it. Apparently, I didn't think about this. So all intents and purposes, just cross that out and write LDA. So this is kind of the reaction we see. So Br2 in light, as you know, that's regioselective bromination. That's going to add the bromine on the most stable position. So that's clearly the tertiary. So I'm expecting, some structure like that. LDA is a bulky base, so I'm expecting the Hoffman product or something that looks like this. Okay. This is just acid catalyzed hydration. So I'm expecting, water to be added, in that middle or that tertiary position. Okay, and then from there it's just Tozo Chloride, and since this isn't a chiral center, I can just write again, oops, OTS, nice and easy. Step 3 was just acid catalyzed hydration. That was just adding an alcohol to the alkene on the secondary position. That was it. Yep, pretty easy. Again, there's nothing more into it. Okay, so dehydration of alcohols. Let's keep, Maria, what's the question? What did you do in step 3 for the question above? That was hydroboration oxidation. So that was anti-Markovnic addition of the alcohol. So that was adding the alcohol here. And then the last step was converting it to that Ariel sulfonate, OTS. Okay, that's really it. Okay, that was it for that reaction. So again, reaction 6, I think it's, again, just, for me, it's stupid. I don't know why it's like in the curriculum, but it's just another means of making that a good leaving group. Okay. So what you could do is essentially do more reactions. So I can take this, and then what I can do is basically say Na3, DMSO, and I exclusively get, that from that. Okay. So you can see, you can keep playing with your stereochemistry to keep going back and forth and back and forth and back and forth. Okay. So that's that. Then we're going to move on to the last 2 reactions. So we have dehydration of alcohols next. Okay, so we're doing great. So dehydration of alcohols, and this one's kind of a tricky one. Okay, so essentially what you want to imagine is that you have some sort of alcohol. Okay, and essentially you are going to subject this to acid, which is typically sulfuric acid. That's what we see here. And you're going to add heat to it, and you're going to drive this reaction to completion by, using Le Chatelier's principle. Remember, if we remove a product, where do we shift the equilibrium? If we remove or we take away, we shift it towards that side, right? So if I take away a product, I shift the equilibrium towards the product, okay? So that would be pulling this reaction to completion, essentially. So what do you imagine happens? Well, first, I can imagine that this alcohol is going to get protonated by that strong acid. So then what you're left with is basically the conjugate base of sulfuric acid. So that's basically, it looks like that. And what you can imagine is basically in E2 fashion, is we're going to be able to, oops, I can just try here, is we're going to be able to remove a proton, donate that electron density into the ring, and facilitate the removal of the alcohol to basically form your alkene. So E2 fashion. Okay, so you can basically go backwards from an alcohol to an alkene by doing dehydration conditions, and you can see probably how useful this is. So imagine in synthesis, I were asking you this. Actually, it would be, let me think real quick. Okay, if I wanted you to go here to something like that, okay, you would have to essentially go to an alkene first, okay? So yeah, you would definitely have to dehydrate, okay? And once you dehydrated, you could have been like, oh, I needed to extend the carbon chain. And I only know one way to extend the carbon chain. We've seen this over and over again at this point. And if I have to add it by 2 carbons, that's just going to be 2 carbons. So then you get the acetylide. So 1, 2, 3. So it's between 1, 2, 3, 1, 2. So you're there, and then you just have to reduce that to, NH3, because that's the E alkene. So again, it's basically an extension. Your synthesis this time is going to be an extension of things you've already seen, but just making sure you have an extra step in there. Okay, that's kind of like a good place to be. So yeah, so that's basically how this reaction forms. But, you know, in more substituted alcohols, let's say I had, you know, an example where we had, let's just do here, benzene. Okay, and I had an alcohol here, and I treated that to the same conditions. Okay, so essentially what you can imagine is this gets protonated to form that. Okay, that's the water. And then the conjugate base of sulfuric acid, HSO4 minus, could do one of 2 things in this situation. It could do the E2 fashion, like we saw, removing it because, you know, it can't leave on its own, because the carbocation wouldn't be stable. Or if we can form a stable carbocation, the leaving group can leave in an SN1 fashion. Okay, we get this, you know, secondary carbocation, but because, you know, we go through this intermediate, of course we have rearrangements possible. Okay, so we get this tertiary benzoic carbocation, and then now that that proton was moved, we can get this Zaitsev, you know, elimination product where we have HSO4 minus comes in, removes that, and we get this alkene. Okay, so just remember that carbocation rearrangements are possible. This is just yet another example of how to convert an alcohol to an alkene. All right, let's just do an example of that. So let's look at, I'm at letter AA on 114. Okay, so we're thinking definitely elimination here. This could be either E1 or E2, but we'll see. And remember that elimination specifically is going to follow, yes, only assume one rearrangement, Brian. And this is specifically going to be a situation where I need to have that same anticoplanar logic from the last chapter, okay? So remember, in rings, it's pretty obvious to find that you're looking for a hydrogen on the opposite configuration than your hydroxide or your leaving group. And I can prove that to you by showing you this chair conform. If I call that 1 and 2, 1 is down, 2 is up, that's 1 and 2. And that's the nice orbital arrangement for us to be able to facilitate that removal. And essentially this gets protonated, and then HSO4 minus can just remove that, donate that in, remove, and you actually get the Hoffman alkene, okay? Yes, I like that. But if it's SN1, will it range? Okay, so this was me assuming E2 conditions, right? But is it E1? So we really need to like see that. It could be E1, and if this carbocation leaves, I'm sorry, if that water group leaves on its own, then you're here, and then you still have that hydrogen here, and then you can do this hydride shift there. I haven't seen that before. Let's see. And then now you have a carbocation at the tertiary position, and then the base could actually form the Zaitsev. Yeah. And okay, so that's a great question, Charles. And honestly, I don't have a great answer, and I'm not going to pretend that I do. But what I can tell you is this. You have two pretty decent options, okay? You can argue SN1 or SN2. So let's just kind of follow my logic, and hopefully that helps you. You can follow, you can follow either E1 or E2, is what I'm saying. It seems like in this condition. But remember, there's no limitation here in terms of bulkiness. So, you always want that more substituted or more stable alkene. So really, by trying both pathways, by showing the E2 product and what the potential E1 product would be, I clearly get a Zaitsev more substituted and the Hoffman less substituted. So on my test, if I were in this, this gray area, which we're typically used to when we have secondary materials, then I would honestly pick the Zaitsev one, because the Zaitsev one is, arguably just as equally as happening as this Hoffman example. That's probably the best example, the best logic I could give you. Sorry. Yeah, bye Keisha, hopefully that helped. All right. Does that help you, Lauren, a little bit? Not stressing you out? I really don't have the best answer. They can arguably happen either pathway. And for me, I kind of see that the Zaitsev one is more stable, more substituted. So that's why I picked that one over the Hoffman. Yeah, if you don't figure it out, ask Dr. Peterson or Habinix, they can probably elaborate. All right, so let's just finish up. So that's kind of dehydration of alcohols, it's prone to rearrangements, things like that. And then the final thing is just oxidation. You guys will like this, and you're going to pick up on this in Orgo 2. But essentially, you have two main schemes. So this is that. Two. Okay, and you're going to basically fill this in Orgo 2. So in Orgo 2, you're going to be able to go, from here to there, from here to there, or from here to there, or there to there. So you'll get more arrows, but as of now, this is kind of all we're at. So basically, this is considered weak oxidation. Okay, this is considered strong oxidation. Okay, so you can imagine that, we can either, have weak conditions and go to the first product, or have strong conditions and bypass the first one and go to the second one altogether. So that's kind of indicative of the specific reagent that I use. So the weak reagents we use is something called PCC and DCM. Okay, DCM is that same solvent, dichloromethane, but PCC, that's the only one we know that's a weak reagent, so just use that one, okay? And you don't need to know the Lewis structure or anything like that. It's PCC and DCM solvent, okay? Strong oxidant condition, there's a whole bunch of those. So the chromates, the family of dichromates, so these guys, and you might see these a lot. Sodium dichromate, it could be substituted for potassium dichromate. You could see Jones's reagent, okay? Okay. You could also see, I think we also have sometimes HCrO4. Okay, so these are all just strong, notice they're metals and there's oxygen, so they're strong oxidants. Okay, so these are all the types of strong oxidant, and you'll see the word Jones's reagent, okay, the word Jones's. Okay, so those are the differences in conditions. So essentially, if I draw in, the protons here, okay, the Orgo definition, so back to Gen Chem. The Gen Chem definition of oxidation reduction was oxidation is the loss of electrons, while reduction is the gaining of electrons. It's different in organic chemistry. Okay, we have a different definition now. It's not oil rig. What it is oxidation is the loss of a carbon-hydrogen bond, but the gain of a carbon-oxygen bond. Whereas reduction is the opposite of that. So it's the gaining of a carbon-hydrogen bond and the loss of a carbon-oxygen bond. So that's the organic definition, okay? It's just kind of like how the Arrhenius definition is a bifurcation from, the Bronsted-Lowry or the Lewis definitions. So this is just another way of looking at that same reaction that goes on, but following something else, meaning the electron movement in the bonds framework, to basically categorize these reactions as such. So anyway, we're going to basically oxidize. So we're losing these carbon-hydrogen bonds, and in their places putting carbon-oxygen bonds. So essentially, the first step from a weak oxidation would basically be to form this aldehyde. Notice that it's still 2 carbons, 1, 2, but we lost a carbon-hydrogen bond while gaining a carbon-oxygen bond. So that's the first oxidation that we went to. And then if I were to do this one more time, you can remove that final proton and maybe in place of that, put another oxygen bond and make a carboxylic acid. So these are the 2 products that you basically get from these reactions. If I were to take, a primary alcohol, and that's important, if I were to take a primary alcohol and treat it with a weak oxidant, I get this aldehyde. And if I were to treat it with a strong oxidant, I get a carboxylic acid. Okay? And if I were to basically change the substitution of this alcohol, you get very different products. So let's think about that. Let's take a secondary alcohol, for example. Okay, so this is clearly secondary. And I'm going to treat it with PCC. Okay? Well, notice I have 1 proton available, so I can definitely remove that in an oxidation. And we don't go through the mechanism, but we can remove that proton and then form a new carbon-oxygen bond, basically forming a ketone, okay? So I can do that. But now if I wanted to basically do the extra round, which would be involved, if I had, in the stronger oxidant conditions, let's just say this is basically if I had, Jones's reagent or something like that, I only had 1 proton available, so I still get the same product, okay? I stop there. I don't have any more protons available to keep going to that carboxylic acid. Okay, do you see that? I only had 1 proton, so 1 round of oxidation. Here I had 2 rounds of oxidation. Now let's go to that tertiary guy. If I had a tertiary where there are no protons available, and let's say I did PCC and DCM, no reaction. Let's say I were to do this with Jones's reagent, no reaction, okay? So you can see that a condition for these oxidation reactions is those protons available, okay? So this is super easy in my opinion. So let's kind of just go to some examples. So let's just look at, and this is it. This is the end of the chapter. Okay. So essentially, let's just look at DD. And we're treating this with a strong condition. So basically, this is the sodium dichromate. So these are strong oxidation conditions. So I'm just going to write strong. Okay. And everything that's in every alcohol is potentially capable of being touched. So if this is a primary, we know it's going to go all the way to the carboxylic acid. If this is a secondary, we know it's going to go to a ketone. And if this is a tertiary, nothing's going to happen. So essentially, what does that translate to? Well, you can basically just draw this. Okay, so notice the primary one had 2 protons. So both of those protons were removed in 2 rounds of oxidation to basically get the carboxylic acid. We saw that right here. Okay, there are 2 protons, so the first round removes the first one, then you get an oxygen bond, and then you add another oxygen bond. So that's the carboxylic acid for the primary. The secondary, there's only 1 proton, so we have to stop at the ketone or the carbonyl. And then the tertiary, there are none available, so we can't even do anything. Okay, so that's basically how to do this. Okay, let's try FF. Okay, so let's okay, so this is PCC and DCM. So this is a weak conditions, okay? So only 1 round possible for each of these. So here's one of those protons available at this secondary position. So yeah, I can definitely remove that and form a carbonyl. Same thing here, same thing here. And here I have 2 protons available, but remember it's weak conditions, so only one of them is going to be removed to form the aldehyde. We're not going to go to the carboxylic acid there. So what does that look like? Well, here, here, and we actually stop at the aldehyde. We do have this extra proton, the aldehydic proton, that we could remove to keep going, but we're not, okay? So we're there. All right, and yeah, that's FF. Let's just do HH. Okay, so we have phenol with this this methoxy substitution basically, and it looks like it's K2Cr2O7, an acid. Again, this is another strong condition. Okay, so anytime we see phenol, okay, it's part of benzene, does not react. We don't touch benzene until orgo 2. So we have strong conditions. So basically you can imagine this phenol stays on and you get this carboxylic acid forming, this benzoic acid. Okay, pretty easy. And that is the end of chapter 10. Okay, so I definitely have worked your brains, I think, enough. Basically, we're going to stop there and just keep practicing SN1, SN2, E1, E2. Will you post Wednesday soon? Yeah, I'll probably try and post both these today. This is the end of the chapter 10. And I'm trying to think. Do you guys have epoxides on your chapter 11 on your final? Or no? Oh, good. But not on exam 4. Okay, cool. So we're basically just done with exam material, which is good for the most part. So Wednesday, we're just gonna basically do a big exam review of everything. So I'm gonna post this on Canvas. I'll tell everybody we're gonna do an exam review. I'm gonna post Wednesday's lecture and today's lecture up onto YouTube. And you guys will be going for your test on Friday. And then the following week, we'll do one big final review. All right, see you guys.